Hi everybody, this is my Encyclopedia AI channel. Today I'm going to introduce to you a paper called Mutual Information Neural Estimation. This paper comes from ICML 2018. The authors are Belghazzi, Baratin, and we also see Yoshio Bengio as the co-author. In this paper, a deep learning approach to estimating mutual information between two random variables is offered. Specifically, in deep representation learning, maximizing mutual information serves as the principle of compressing information from your raw data into its representation, also known as the embedding. However, computing the exact value of mutual information between two random variables is notoriously hard. Actually, the idea behind this paper is both inspiring and interesting. It first finds a lower bound to the mutual information and then uses a neural network to represent any function in a functional form. In such a way, it links a neural network to computing the mutual information. Before proceeding, let's first have a quick review of what mutual information means. The mutual information between random variables x and z is defined to be for each pair of x and z, take its joint density, joint probability divided by px times pz. Then take the log and weighted by pxz. The definition is equivalent to x and z's entropy form, which is the entropy of x minus the entropy of x given z. It is also equivalent to entropy of z minus entropy of z given x, since x and z is symmetric. What's the meaning of mutual information in this entropy form? First, we notice that the entropy of x is greater than or equal to 0. And second, we notice that the entropy of x is greater than or equal to the entropy of x given z. Why it's true? Because we know that entropy measures the uncertainty of a random variable. In case x and z are independent, knowing z gives us no hint of guessing x. So in this case, the entropy of x remains the same. It's equal to the entropy of x conditioned on z. Take an extreme case, for example, if z is the x itself, so knowing z gives us perfect information of x, then the entropy of x conditioned on z is 0 because there is no uncertainty. So correspondingly, the mutual information of x and z is the reduction of entropy in x if we know z. It's this reduction, information reduction. The entropy form of mutual information has physical meaning, but it's very hard to compute mutual information in this way. So in this paper, the mutual information is represented the second way, which is the KR divergence between two distributions. The first distribution is x and z joint distribution. The second distribution is the product of x and z's marginal distribution. Then the paper resorts to a functional form of the lower bound to the KR divergence, which is known as Donsker-Varadhan representation. The representation is defined here. It is for any function t which has the same domain as p and q. For any function, this expression is always less than or equal to the KR divergence. The proof is simple, so let's prove it on our own. In this proof, we replace the function t with function g, which is defined on domain X. We also have two distributions P and Q defined on domain X. We also demand that the expectation under Q distribution of this G expression is finite. And then we construct a new function Z, which is a function of G, and is defined as this expression divided by the normalizer, such that not the Z in expectation under Q distribution is 1. Then log Z in expectation under P distribution can be written in this form. Notice that we introduce Q of X in both the denominator and the numerator position. And now the first term can be written in the form of KR divergence of P with respect to Q. The second term is in the form of expectation of a log expression. From Jensen's inequality, we know that it's less than or equal to the log of expectation. The last step is we cancel P distribution and use Q distribution in expectation. Rearranging the left and right terms, we have the KL P with respect to Q is greater than the EP log ZG minus log EQ ZG. We notice that this term is 1, so take the log is 0. So this term cancelled. And substitute in the definition of ZG here. We have this term is equal to the EP. The first term is the log of the E, so it's the G of X minus EP of the log of EQ e to the gx, and this expression can be simplified as the log EQ EGX. So here is the Donsker-Veridum representation. And we completed the proof. Here we link everything together. Now we have the mutual information in the form of KR divergence. The KR divergence has a tight lower bound in functional form. So in summary, the mutual information between X and Z is greater than or equal to the sub of all function t. Now t maps xz to real number. So t takes in two variables, and the first term is the expectation p. Now p is the joint distribution of z, x and z, this t, minus the log of expectation under q. Q is a distribution generated from the product of two marginal distribution px times pz. This expression is the e to the t xz. Finally, let's see how deep neural network can approximate this lower bound. In typical representation learning setting, we have pairs of x and z, which means we have the joint density of pxz. From this joint density, we can also generate pairs x and z following this product of marginal distribution. And we employ a neural network with parameter theta to represent an arbitrary function t theta. Now we have everything we needed to employ a Monte Carlo method to compute or approximate this expression. We have pxz, we have t theta, we have q distribution. If we view the whole expression as a function of theta, so it's denoted as f theta. The ultimate goal of the training the neural network is to find theta prime, such that the maximum value of f theta is achieved, which is the tightest lower bound of mutual information of xz. Till now, we should be very clear about how the algorithm works. We are given an algorithm which learns the representation of x and outputs its representation z. Our goal is to estimate the mutual information between random variable x and z produced by this algorithm. And now we come up with a neural network parameterized by theta to represent a function t whose parameter is also theta, and it takes two inputs, x and z, and outputs a real value we train a neural network to learn theta prime, which corresponds to t theta prime. And this value has the best lower bound or tightest lower bound to the mutual information. Note that all the samples of x and z are generated by this fixed algorithm. So we can have samples of pairs x and z following the joint distribution pxz from this algorithm. In addition, we can draw samples z bar from margin distribution pz by merely dropping x from all the pairs generated. Finally, we evaluate the lower bound by computing this value or evaluating this expression. The first term is the value generated by our neural network whose input is the pair of x and z drawn from joint distribution. The second term is the value output by our neural network whose input is xz pair. Note, we pair x with the independent marginal z. Finally, we update theta in the direction of increasing the lower bound. This is the implementation of my algorithm estimating the mutual information using a neural network. There are other details in this paper, like correcting the bias from stochastic gradients. I leave these to you and let you figure out these details. If you like this video paper sharing, you can subscribe to my YouTube English channel or WeChat Chinese channel. There will be more about deep learning, reinforcement learning, and statistical machine learning in my channels. Thank you very much. See you next time.